8, but I'm still chapter 7. And some of you maybe still chapter 6, 5, 4, 3, 2. But slowly, you have to hurry up and come and catch me. As we started in chapter 6, we are trying to discuss about the convection. Convection, we just went through very basic information to show you how actually they calculate the heat transfer coefficient. The way we did it, they write mass balance equation, momentum equation, and energy balance equation. First, they find the velocity profile, and they put in the last equation for energy, and then find the temperature profile, and then understanding that the velocity at the very close to the boundary layer, that heat transfer is by conduction, and then trying to find the slope of the temperature and then calculate that. That was the procedure we went through it, and we show you how to come up with the heat transfer coefficient. On chapter 7 and 8, we are going to discuss about different application. And the first one, we're looking about external flow force convection. Therefore, yes, the last one we had, it was for a plate that we were able to visualize the velocity profile, we were able to visualize the temperature profile and try to understand the relation between them. But now we are going to further to different geometry, like a cylinder, like a heat exchanger, and so on. But before I will start, I would like to go back again and look at this problem. And just review chapter 5, okay? Remember chapter 5, it was dealing with a numerical technique. And here we would like to consider two-dimensional heat transfer. This is from your textbook, problem 5151. Therefore, you don't have to write it down. If you have your textbook, please open your textbook and take a pen and pencil and start to do it. Therefore, this is two-dimensional. We didn't do anything before about two-dimensional. Therefore, I'm just coming back and trying to just give you a sort of a practice. Okay, we did it one-dimensional, but the question two-dimensional, now we have to write sort of energy balance in X direction and Y direction. Therefore, we have a solid bar, two-dimensional. It has a conductivity of 25. And the dimension is 2 centimeter by 2 centimeter, which heat generate inside the ball. Therefore, we have a source of heat generation inside the system. The left and bottom surface maintained at the constant temperature of 200 degrees. The top and right surface are subject to convective heat transfer of ambient of 100 degrees. Therefore, the heat transfer is 250. And using the sort of the case that we have, we assume, again, you don't have to do it, but this is just simplified the hand calculation, that we assume the mesh we had, the distance between node is 1 centimeter. Just take your book and look at it and try to do this problem, okay? This is the case that we have. We have a two-dimensional, here dimension given 2 centimeter by 2 centimeter. This side and this side are kept at constant temperature of 200 degrees. This one, the whole surface is 200 degrees, and here the whole surface is 200 degrees. Okay. Here we are dealing with convective heat transfer, and here we are talking about convective heat transfer. Therefore, this side and this side are exposed to convective heat transfer. This side and this side is 200 degrees. We would like to write it. Expression for node number 1, 2, and 3. Okay, 1, 2, and 3. Could you please do it again? This comes from your textbook, and I believe I also mentioned how much is the heat generation, but somehow at the rate of I believe is missing from my part. Okay, here's missing. But if you look at the textbook, it will give you amount. The only thing I need at this moment, if you please write down equation. For node number 1, 2, and 3. Okay. And therefore, we know the dimension, 2 by 4. We know the conductivity of material. We know this here is conduction. And mention the temperature outside and mention heat transfer coefficient. And we know this boundary and this boundary are at constant temperature. And also mention there's in some heat generation inside the system. Therefore, we have to make some assumption. Again, this assumption just to be, when we write the equation, we know what term we have to consider and what term we have to ignore. We assume this is a steady. It means there is no energy accumulation in the system. It is two-dimensional. We also assume the thermal property are constant because this is again one assumption that we are making, that it means, for example, the conductivity is constant. Therefore, you can easily mention the conduction is equal K dt over dx. And heat generation is uniform. Therefore, heat generation is not a function of the temperature, it's not a function of the position. And also the information is given here. Therefore, here we are trying to analyze this the problem. Mention that we have 1 point here, 1 point here. The distance is 10 centimeter, 1 centimeter, 1 centimeter here. Okay, therefore we know the distance here. And now we have to sort of specify that for each region. Therefore, what we have to do, we identify the boundary for each. Therefore, this portion represent node number 1. Okay, therefore this portion represent number 1. This portion represent temperature 2. And the same thing we can do it for node 3. If I draw another line here between, represent here. This therefore this is interior node, but the main concept we have to be here when we write the equation for exterior node. Okay. Okay. Therefore, we have conduction from node from this temperature here is with this node here to this one. Therefore, from here to here is delta x, but the area is heat transfer is only this part. Therefore, it's delta y over 2. The same thing from node number 2 to number 1 is again is conduction. The distance between these two is delta x. Again, the area for conduction is through this layer here, this part, is delta y over 2. This node exchange radiation energy by convection. Therefore, is h delta x from the distance between this portion and this one is delta x, and times temperature difference. And then we have from node 3. Therefore, if I want to write it down, node number 1, I have here. I have convective heat transfer to this surface. Therefore, is delta x times 1 L, whatever it is. This is the area, temperature difference. Then I have point 2 to 1. The distance between 2 is delta x. The area represented by half of this, okay? Because from here to here is delta y. Therefore, here represent node number 2, becomes delta y over 2. That's we have to keep track of them, okay? For node number 3 is interior node, because the distance between here and here is delta y, and the conduction surface area is delta x times 1 over L. And the same thing from node 200 here, from this point to this one, okay? Any question? Plus, how much energy generated in this volume, because this is per unit of volume. Therefore, delta x here, this is delta x, times delta y over 2, here, this length, and times the other length we can assume is 1, okay? Therefore, this represents the volume, and this per unit. Any question about this equation? Please don't be shy. Ask me if you have any question.
Sir?
Yes, sir.
Why are we taking delta y over 2 again? Is it not
Here?
the area?
Here?
Yeah.
This sir? Because the heat transfer is perpendicular to that surface, okay? Assume from node number 2 to node number 1. Therefore, okay. Here is the cross-section area, this heat transfer from here to here. Therefore, it's perpendicular to this area. This is represent delta y over 2, and the third dimension is L. We assume is the length is L. Okay.
All right, I got it. Thank you.
Same thing, the same thing that we have for node number 1 here.
Yep.
Okay. Good, sir. Then let's go to node number 2. Again, node number 2, again, we're writing conduction from node 1 to node 2, conduction from node 4 to node number 2. And this portion represents node number 2 is convective heat transfer here. And this portion here, delta Y over 2, convective heat transfer here. Could you please write equation for node number 2, please? For node number 2, energy conduction to node number 1, conduction to node number 4, convection to this side, convection to this side. If I write it down, it's become like this. This term is representing of the convective heat transfer to this portion, delta X over 2, plus this portion, delta Y over 2. Therefore, we combine them together because temperature is infinity here, temperature is infinity, heat transfer is H and the H here. Therefore, this represents H times this two part, one portion from the top, one portion from the side, and that's times L or 1, okay? And T infinity. This equation represents conduction to node number 4. Code node number 4 right here, okay? Conduction from here to here. Again, heat transfer from 1, 2 to 4 is the perpendicular area, and that's delta X over 2, because this portion represents node number 2, okay? And that's exactly right here, you see here. And the last part is from node number 1. Again, conduction is perpendicular from 1 to 2. The area is this part, okay? This represents delta Y over 2. And here again, it represents the volume of this portion. Delta X over 2, delta Y over 2, multiply, give you this area, and multiply by L that we have here. Any question this part, please? Any question, please? Now let's go
Sir?
to number. Yes, sir.
It's written E generation 1 and 2, but they're all the same, right?
That's right. Each generation number 2. That's right.
Okay.
Each generation remain constant. Absolutely right. Correct, sir. Is the same value. And here for node number 3. Node number 3 is easy because it's interior node. Conduction from here to here, conduction from here to here, conduction from here to here, conduction from here to here. Here the temperature is constant 200. Here is a constant 200. And here is conduction from 1 and 2. Okay. Therefore, you can see this is simplified equation that we get to this part. Therefore, please practice. If you have any question, ask me. Okay. Again, we will come back and randomly take problem number chapter 4, 3, 2, 5, 6, and do it in the next future classes. Okay. But the only time is good if you go through it. If you have any question, ask me. Okay. Okay, let's continue. Any question, please? Let's move. Therefore, as I mentioned, we are chapter 7. Chapter 7, we are looking about a convectivity transfer, force convectivity transfer exterior surface, okay, outside. We discussed in detail in this scenario. For a flat plate that we have air fluid is coming, gas is coming here, and slowly the velocity profile, and we have a boundary layer right here, okay? So this shows the velocity profile. This shows the velocity profile here as slowly improve, and here we call this boundary layer. But also air can come perpendicular to a system, like a wall, okay? If you have air comes here, it's not going along it, but here now we can see the air comes here, as you saw in building science, air jump over here, and depending on the velocity, will jump back here and create some recirculation of the air, okay? Here is positive, represent the velocity is positive, pressure is positive. Here is pressure is negative. Negative, it means compared to main stream that we have here, okay? Therefore here, the air rather than going this direction because it's low pressure, it come back and recirculate here. Therefore, we expect the heat transfer in this scenario will be different from that one. Therefore, we are trying to look at different application. Another one that you can hear is car, okay? Therefore, the car is moved, okay? And here, for example, it shows the wind tunnel, they're measuring, and look at air velocity here is different, and depending on the shape of the car, we can have different pattern of the boundary layer that we have over there, okay? Here, probably is become like this, in the back, become like something else, okay? Because here this has a dimension, okay? Therefore, we have some recirculation. Therefore, they're trying to, in the design of the car, they're trying to make it smooth, this boundary layer that reduce the pressure, okay? And if you look at the heat exchanger, we have this scenario. For example, you have a pipe here, the fluid, for example, water goes inside, oil goes up, and then you have outside the wind come and other fluid come here. And you can see here, this is the high velocity, the velocity is jumping up here and then coming back here and create the pressure. Therefore, you expect the profile of this velocity will be absolutely different from here, okay? Because here is round, probably is smoother than this case. Now, we're how to calculate the heat transfer for this scenario, okay? Probably numerically it's easy, but analytically very difficult to do that. Therefore, in most of the time, we use a combination of experimental approach trying to find the heat transfer this way. And you have a case that you have not only one pipe, maybe you have too many pipe. That's exactly heat exchanger. Here inside, these are the pipe that there is, for example, fluid is passing, and here outside is air trying to cool it down, okay? Therefore, the velocity profile when reach here is different from here. Therefore, we can see the velocity is not as smooth that we had it here, or uniform as here, or uniform as here. In this scenario, the velocity now is interrupted, therefore the heat transfer will be different. And again, it depends on the design and arrangement of the heat exchanger. Look at here, they're very nicely placed, but here we have different arrangement of the pipe, okay? Now, therefore you expect the heat transfer in this case will be different from here. Now, in design of heat exchanger, we need to know the value of heat transfer coefficient. In most of the question, how we do that. It's very difficult to find an analytical solution. We can calculate numerical, but numerical it cannot be designed at every time we would like to design. Therefore, we're trying to use experimental technique to find a average heat transfer for this scenario, okay? Therefore, you can look at here, we're looking external, we're looking external, external. We don't look at inside, but looking outside the pipe, okay? Outside the pipe, how to calculate, okay? This is the case. In this chapter, we're trying to find an equation to be able to calculate the heat transfer for different scenarios that we have here, okay? Again, we are trying to give you an equation. We are not going to use any more mass balance or energy balance because I know you will fall asleep, but give you the end result. This is the purpose of this chapter. Look at this problem. Again, this is an application that we need them. Look at here. This is the way to test the car. Look at read the problem. You don't have to solve it now. We will come back to here. Again, we would like to design an air conditioning system for a car. Okay, that's exactly, you will find a summer job. The system is trying to maintain, you would like to maintain the inside the car at 20 degrees. When the car travels 100 kilometers per hour. Again, the temperature outside is 30 degrees, and at night, because we're trying to simplify the problem, that ignore the effect of solar radiation. We only would like to look at the convective heat transfer. If the top of fan can be idealized as a flat plate, 6 meters long, okay, and 2 meters, and wide side is 3 meters. Therefore, the car is 6 meters by 2 and 2 by 3. Estimate, what they're asking you here, estimate the rate at which heat must be removed from interior in order to keep the temperature comfortable at 20 degrees. Therefore, again, this don't try to do it right now because we do not know the equation, but at least this is one of the application. We know the velocity, but we do not know the heat transfer coefficient, okay? Therefore, somehow we have to develop a methodology, a technique to calculate the heat transfer value, okay? This is the idea we're trying to do. We know the velocity because we know the car, we can look at the velocity, but we do not know what is the heat transfer coefficient. That's what we're trying to do, okay? Look at another application. Again, another application just to show you what we are going to study. Combustion air is in a manufacturing facilities to be preheated before entering a furnace by hot water at 90 degrees. Therefore, through a tube. Therefore, we have tube heat exchanger, a series of them, a number of them. We pass the air to preheat it in order to improve the efficiency of the furnace. And what atmosphere here? The air comes with this one and flow over the tube. Exactly as I mentioned, it's heat exchanger. We have a tubes, number of the tubes placed. We pass air through them to preheat it in order to improve the performance of the furnace, okay? The question here is how much heat has been transferred, okay, to the air, from the tube to the air, okay? Therefore, this is, again, exactly what we are trying to do. We are trying to look at either this scenario or we're trying to design the HVAC system for this car. We know we're going with 100 kilometers and how much energy is removed from the car. Or we have a system like this, we pass the air and we know what the temperature is coming here. We know what is the temperature of the water here. We would like to see what is the temperature of the air when enter the furnace, okay? This is the application we're trying to look at it. Exactly like here. You have a heat exchanger, air comes here, pass over this fluid. These are the pipe, hot water going here. We would like to see what is the temperature here before we get to the furnace. Now the question here is, heat transfer is from the air to the tube. How much is the heat transfer coefficient between the air and the tube? We do not know. We're trying to come up with some equation to be able to calculate this value. Any question, please? Is it clear to you what we are trying to do? I hope. Let's move to the next slide. Therefore, when, again, I always put this, when we finish this chapter, not now, we're trying to look at here is, we would like to understand the flow inside the pipe and outside the pipe. Inside the pipe, we call it internal. Here in this chapter, we look at external, okay? We're trying to, in this case, find the heat transfer between pipe and the air outside. Again, in understanding of the convective transfer coefficient external, we cover this part in chapter 6. We have some idea what is heat transfer coefficient, okay? We came up with an equation to give us the heat transfer coefficient at any point. If you remember, the number was 0.23223, Reynolds number to point something, 0.5, Prandtl number to 0.3. Now we're trying to apply it for other case. This gives you at 1 point Hx local heat transfer. But if I want to apply to my house, I have to find the average heat transfer coefficient. The question how we are going to do it. Evaluate the heat transfer associated with flow over a plate, both for laminar and turbulent. We find an equation that gives us a local value, but now we are trying to find an average heat transfer coefficient. That's exactly we're trying to look at it. Average heat transfer, because the equation that we have give you Hx. Hx, it means at a given point, at x equal 0.5, at x equal 0.75. But now, when I look at the building, I would like to look at how much on average heat loss from the roof of the building. Again, we determine average heat transfer coefficient associated with flow across the tube. Here we're dealing with a single tube, wall, and so on. But when we're designing a heat transfer, we are not dealing with only one tube, as I mentioned before, because there are a number of the tubes, the air velocity will change from one tube to another one. Therefore, in case we have a bank of tube here, you have more than one, the question here is how we can find the heat transfer average, okay? With that. Okay. As I mentioned, we are dealing with the external. You have dealt in fluid mechanics with drag force. At least you know what that means, drag force, why the airplane is flying, power line, and so on. Lift that help the airplane fly. Drag force when pushing the car, and there is a resistance. We can calculate how much is the pressure cost and so on. And also with cooling the metal that we are dealing here is there is heat transfer. There's a heat transfer between outside and inside. Okay. We have also some idea what is free stream velocity. We have this is very important to understand because this we always use it as input for the calculation. This is the velocity before become sort of in contact with the surface, and therefore the effect of the viscosity disappear. If you remember, we had the velocity before that, below that boundary layer, the velocity profile was changing. After that, it was independent of the viscosity of the surface. That we call it free stream velocity. Okay, and this is usually come based on non-slip condition, because in the boundary layer, as you remember, in the boundary layer, we assume the velocity on the surface is equal to 0, and slowly is increasing until we pass the boundary layer. And after boundary layer, we have free stream velocity. It's not sort of affected by the viscosity or the surface plate. Okay. And here we mentioned this is what we learned from previous chapter. For example, in case we are applying, because it's very easy to see it and visualize it, we have some uniform air velocity will come here, and this is my boundary layer. Here is free stream. It means it has not been influenced by viscosity layer. Okay. And based on that one, we calculate and we find an expression like this from the previous chapter. We said this is the heat transfer coefficient. This is local Nusselt number. Remember, this X is not for beauty. It represents a given point, and that given point is given. We'll define local Nusselt number, and that gives us local heat transfer coefficient, and that gives me the point I don't want to calculate. If I want to calculate the velocity here, the heat transfer coefficient here, this is my length from here to here. And here's the constant we discussed last lecture. This is the Prandtl number. We measure only as a characteristic of the fluid that we're dealing. It's a gas or fluid, air, or whatever it is, and that has nothing to do with the rest. And here is a Reynolds number. Okay, and Reynolds number we define that Reynolds number in general term we always define as density, velocity, and a characteristic length divided by viscosity. And the characteristic length is changed from geometry to geometry. Look at here, before we said we have a flat plate, we have vertical ball, and we have cylinder. Therefore, we have to be careful when defining Reynolds number. It depends on the shape that we are dealing. Therefore, here we are discussing free stream. These are the free stream. They are not influenced by the fluid and so on, viscosity of fluid. Okay. Now, the question here is this given at one point. When I want to design, I want to find out the average heat transfer from here to here. What is the average? I can calculate every point from here all the way to the end and then add them up and divide them by the length. That gives me the average. Okay, but we can do it here is by defining this expression that we have. Exactly here is we integrate. It means we sum up a different point from 0 to L, and we divide it by L, the length of the plate, and this gives me the average heat transfer coefficient. Therefore, please make sure when you're doing the calculation and you're trying to solve the problem, if you're looking at one specific point, this is we call it average, or you would like to calculate the average heat transfer from this plate. Okay, therefore that's gave me the average here. Therefore, if I use different value of X here and calculate Reynolds number and add them up together, integral, add them up, and then divide it by the L, give me here. But we already have an expression here that is a function of X. Therefore, I integrate this as a function of X and divide it by that one. Okay, therefore that's easier to do it rather than doing hand calculation. Therefore, here we end up here We know Reynolds number at the distance from X here. That's exactly we mentioned. This is the Reynolds number for flow over flat plate. Okay. Therefore, when I calculate my Reynolds number becomes like this: rho free stream undisturbed velocity, because the velocity here is different from here. But when we calculate Reynolds number, we calculate with the stream right here, and I can change this one, or I can use this equation. This is the same as this one, except this is kinematic viscosity. It means viscosity divided by density. Therefore, you can find this value from the table, you can find this value, or you can directly calculate and find this value, okay? This equation is the same. Again, we are using the general term of Reynolds number, this characteristic length for flow over a flat plate. Characteristic length is the length of the plate. And this gives you the Reynolds number at a specific point. At the specific point, if I put X, give me that value. But the question here, as we discussed, we have at the beginning, we have laminar flow and then become turbulent. Therefore, there's a length here. We call it a critical length. It's not only one specific. In reality, it's like this. In reality, we have one range, laminar. Then we have a transition period. There is a certain length from here to here, and then from here we become turbulent. Okay. Here is transition, depend on many factors. Therefore, in order to the calculation, we mentioned, okay, let's look at this part we have. We have a length that gave me from laminar to turbulent. And that's, as we discussed last lectures, 500,000. It's not 2,000, 2,000 only for flow inside the pipe. This outside for flat plate, only a flat plate, horizontal is 500,000. Therefore, this we call it critical length. This is the length the velocity will change from a laminar to turbulent. Okay, this is just trying to simplify. As I mentioned, that we have a transition between, but here we're trying to ignore that one. Okay, therefore the actual value of the engineering critical Reynolds number may change from here to here, because again, it depends if you consider transition part and exactly what happened. Okay, therefore this is the range we are considering. That before this value we have a laminar flow, and after that we have turbulent flow. Okay, therefore this is critical length. Therefore now we have again an indicator, the same thing that for fluid mechanics, that you have which flow is laminar and which range is turbulent. Again, in here, again, these are drag force that you can read, but I'm focusing on this one part. We have seen it before. This is the thickness. Thickness, again, here is the thickness of the boundary layer. Therefore, for we're dealing with velocity, remember we had the boundary layer thickness for velocity, and we have thickness for the temperature, boundary layer for the temperature. Okay, this is for velocity at a given point. For laminar flow, you can calculate here, and you have only the result here. This is for turbulent. If the flow you calculate, the Reynolds number is more than 500,000 in this range, you can use this expression to calculate the thickness of the boundary layer. Okay, therefore this here it gave you some numbers, some equation that you can calculate. Okay, now let me go further. If I look at here, as I mentioned, we have already an expression to calculate local Nusselt number. Okay, for laminar, it was this equation, and now in this chapter also going to give you value for turbulent. Okay, just accept it as it is. We are not going to derive the equation. Look at here, Nusselt number, x, both of them, this coefficient, just for your general information as engineer. For laminar flow, is a power 0.5. For turbulent, is power 0.8. Therefore, this just for give you a general engineering knowledge. The flow over flat plate, Reynolds number is 0.8. For turbulent, this one here. You don't need to memorize it, just to know this is the way it is. And this equation, again, you have to remember, we have a condition. In case this equation is correct when the Prandtl number is more than 0.6. I hope you remember what that means, Prandtl number, okay? Again, this is a physical characteristic of a gas or fluid. It depends on CB, K, and density, okay? That's only. And this is for the case of 0.6 and less than 60. Therefore, whenever you're trying to use equation, do not just blindly apply it. This is only applicable in this range. If you get involved in design of any process and so on, this is just information, but you have to go to the library, look at the handbook of heat transfer, and there are 10 volume heat transfer and give you more accurate number than this one. This is a general number, okay, for a wide range that we have seen here. Exactly, if you would like to visualize it, the trend is here is at the beginning, you have an infinite heat transfer value, and then slowly drop here. This is the value of the behavior of the heat transfer. Okay, it slowly drop. In transition point, again, increase suddenly, start to mixing take place, and then again become steady turbulent flow, slowly drop. Therefore, these two equations, their behavior, the pattern is like this. Slowly drop right here as X, because remember here Reynolds number and here the value. Therefore, keep in mind these are local. This is X again. This is X again. Okay, these are local, and these are the Prandtl number. Prandtl number is only characteristic of the fluid that we are dealing. Okay, therefore now we have equation that we can calculate the local heat transfer, local transfer. Again, this is general information. The fluid heat transfer here, the heat transfer coefficient X equals 0 is almost infinite. Okay, they slowly drop and then will increase. Okay, and this is, you can see here that you have 0.5. Okay, for laminar flow. Any question, please? Any question? Okay. Now, therefore, now, as I mentioned, we are not interested only to look at the heat transfer at one specific point. So in some application, we need it. For example, if you're designing a space shuttle, you need to know what is exactly heat transfer at the beginning, okay, at the top of the space shuttle, okay, if you're dealing with the train, with the airplane and so on. But if you look at the heat transfer in the building, therefore we would like to look at the average heat transfer. Therefore, how to calculate the value average. In the case of this one, this becomes average. Again, didn't come from here. This is what you took the equation before here. We took this equation here. We took this equation here, and we integrated from 0 to L hx. I put that expression here, I integrated, divided by the length, and you can see it's almost become double heat transfer. Okay, therefore here is local, and when I calculate this expression, give me the average heat transfer coefficient. The average heat transfer coefficient is not a function of x. This gives me the average over the length of L. Okay, therefore when you calculate the Reynolds number here, you put the length of the plate. Okay, and then for turbulent, the same thing. You put in the length here, Reynolds number. Therefore, these two values, when calculated, heat transfer is the average heat transfer. Again, keep in mind that when the only time that you can use this expression when it satisfies this condition. Now we have to keep track of all those conditions that we're asking. When laminar flow here, the question here again, let me go back to visualize it here again, please. The question here is we're going from here to here. When I try to assume, okay, just assume this is the plate that you have from x0 to x equal L. Look at here, portion of this plate here, the fluid is laminar. And assume the other portion is turbulent. Here is laminar, therefore I have to use this equation, and from here to here is turbulence, this part. I do not know which one should I consider. If I put x equal L, here is turbulent, but it started from 0 laminar to get all the way to this length here. Therefore, in order to take in consideration the phenomenon that yes, a portion was laminar and a portion was turbulent, this expression that we have here, that satisfies that condition, okay? Therefore, this expression we integrated from 0 to critical length, that change from laminar to turbulent. Therefore, this part, we use the X that we have local heat transfer again. We integrated until critical length, and then from the critical length to end, we consume turbulent. Therefore, if I use both the equation that I have for local and put it here, and I integrate it, my equation become like this. Remember, critical length was 500,000. Now, this expression cover from x equals 0 until x equals L. The contribution of a laminar flow and the contribution of turbulent flow. But if you use this equation, you're ignoring the contribution of laminar flow. Okay? You're ignoring. Again, depend on the top of the fluid that you have, depend on the velocity that you have. Maybe this portion is important, maybe it's not important. But this equation is more complete than this one because it considers the contribution of the laminar flow and the turbulent flow, okay? Therefore, this is sort of a more correct version of this equation, okay? Any question, please?
So basically, you can just use the
Another page, let me just put in mind. Yes, sir.
So basically, you can just use the last equation.
That's
for any
correct.
cases.
This is more accurate, that's correct.
No matter the Prandtl number, no matter the Reynolds number.
It has nothing to do with Prandtl number. The Prandtl number is only for the characteristic of the fluid, okay? Therefore, here is the Prandtl number is included anyway, okay? Both of them is 2 power 1/3. But if it's laminar, therefore you can, it's easier to use this one because we know the fluid is, the flow is laminar. Therefore, there's no contribution of the turbulent. When it's the turbulent, put the preliminary part, the first part is laminar. The question here is how much this critical length? Is it 10 centimeter compared to 10 meter or 10 centimeter compared to 40 centimeter? If you assume the length of this plate is 10 meter, only the first 10 centimeter is laminar, therefore you can ignore 10 centimeter compared to 10 meter. But if you have 40 centimeter and 10 centimeter is laminar, 30 centimeter turbulent, therefore it has some contribution. Therefore, they're trying to look at how much is the contribution of laminar flow to the total heat transfer coefficient. Therefore, this one is, if the flow is turbulent, is more accurate, okay? Because also consider contribution from laminar, okay? Any question? Therefore, now we have been able to develop a sort of, again, you have seen how we obtain this equation, but we are here giving you this part for turbulent. And most of the time, the equation that we have is based as a combination of analytical and experimental, okay? Therefore, they did some experiment with different type of fluid, with different type of gas, with different velocity, and then they obtain some number and they try to fit in the curve, okay? Let's do this problem together. Please read it and try and let's do it together. One of those days is coming, cold winter day is coming. The wind is at 40 kilometers per hour. It's blowing over a 6 meter high and 10 meter long wall. Therefore, is the flow parallel to the wall of a house. If the air outside is 5 degrees and the surface temperature is 12 degrees, determine the rate of heat loss from the wall by convection. Please do it, because this is the whole idea of just practicing. if you have any question, ask, okay? Please talk, ask. I want to make sure that everything is clear to you, okay? You are not in the class anymore. I cannot see your face because I can see from your face how far you are from understanding, but now all the camera is off and I can have no way of understanding the level of your understanding. What should we do, ladies and gentlemen?
Get the characteristic of air at 5 degrees first.
Good. How many of you agree with this gentleman? How many of you agree with Herman?
Guess I'm wrong.
You are either you're wrong or the rest are sleeping.
Yes, we agree.
You agree with him?
Yeah.
Good. At least you have one supporter. Who else
Hey.
agree? You have one vote out of 75. Okay.
42 right now.
Good. You can see the number. Okay, 42. Okay. But why 5 degree? Why not 12 degree?
Because it's the characteristic of the air that's what's laminar or turbulent. The wall is it's just the wall.
Wall is just a wall. I agree with you, but the question, look at here, my friend. This is just the velocity profile, okay? Look at the velocity here is those 12, okay?
At
And
the,
here,
the
at the surface, it was 12 degree, right?
yeah,
Okay. And air is 5 degree here, right?
yes.
But this is just changing. How about the air here? It's not at 5, it's not at 12. Therefore, the characteristic of the air, now in this case, the temperature difference is not that high, okay?
Okay.
In some cases, you're talking about 100 degree and minus 20 degree.
Yeah.
Okay? Therefore, when they developed the correlation here, what they did, they mentioned, let's look at the physical property of the air, the fluid at average temperature, not 5,
Oh,
not,
okay.
not
So
12.
17 over 2. Right.
17 over 2, that's correct.
Okay. All right.
And again, the reason they did it, because again, is based, most of the work has been done is based on experimental work they have done in the lab. They're trying to find those correlations. They find that if they put the average, the temperature is better fit. Therefore, that's from now on, whenever we want to calculate, we look at the average this one. Therefore, we go to table A15. I hope some of you start to open your textbook. And we call it the film temperature, okay? It's not the surface temperature, not the bulk temperature. Not the surface temperature, not the bulk temperature. We call it the film temperature, okay? Therefore, they will look at the physical property of the air at that film temperature and 8.5. In this case, the temperature is not that high, but some cases probably have 60 difference degree, okay? Here's 12.5, but if it was 75 and 5, you could see different. Now we go again. I hope you bought your textbook and opened. At the end, there's a lot of tables, and for A15 give you the physical characteristic of the air. Okay, and that table you can see the conductivity is this, viscosity. Again, this is kinematic viscosity. Kinematic viscosity, rather than looking at what the density and looking at viscosity, we look at one number, and this is kinematic viscosity. And air, again, air Prandtl number is around 0.717273. Okay, therefore that's in this range. Now you have the physical property, and now the question here is, how much is my heat transfer? In order to do that, we have to start to find out what type of flow we have. Again, we are talking about the flat plate and air. Okay, therefore you look at find out the Reynolds number. Again, we are trying to calculate the average heat transfer, okay? Therefore, we use the equation that we have. The first thing we have to do, we have to calculate a Reynolds number. Identify what type of flow we have. Is it laminar? Is it turbulent? We go back, again, mention that I believe that the wall, it was 10 meters long. This is your L, because your tracker, okay? And you mention velocity, okay? Mention 42 kilometers per hour. You change it to meter per second. I hope you know how to do that. Times 1000 divided by 360, give meter per second. We calculate velocity, you have the length, and we have the kinematic viscosity. V, velocity, L divided by kinematic viscosity. And that gives you the value that you have, okay? Therefore, you have 42 kilometers times 1000, change it to meter, divided by this, becomes second. Therefore, this becomes meter per second. And the length, we're talking about the length because the wind goes along the length, okay? This is the length. And here is the kinematic viscosity that we have. Therefore, we find there is around 5,000, okay, 8.2, 5, 10 to power 6. Is it laminar? Turbulent?
Turbulent.
Turbulent. Okay, let's go back again. Let's look at here. It mentioned if it's more than this, we can assume it's turbulent. Therefore, in this range that we have. Okay.
Yeah.
Therefore, let's use that expression that we have to calculate. Okay, what is the number? Okay, let's go on next one. Which is higher than this, that means it's turbulent. Okay, therefore we go and use this equation I mentioned. This equation will consider the contribution of laminar flow and turbulent flow. Okay, I can directly place in this equation because we calculate Reynolds number. We know it's air 0.73, and we place it here and we find the Nusselt number is this one. Okay, what that means? Can you explain what that means? Let's say 10,000. Nusselt number is 10,000. What that means, my friend? Somebody explain to me. Nusselt number is 10,000. What that means? That means the contribution of the convection compared to conduction is 10,000 more. 10,000 times more. Okay. Therefore, you have air is going through here. In general, okay, in general, let's look at here. You have here, therefore, you have a convective and the same time in parallel that you have conduction. You have convective here and you have also conduction here. But the contribution of convection is 10,000 times more than conduction. Therefore, you can ignore the conduction component, okay? Therefore, it's a parallel conduction convection together. Okay, therefore that's the meaning of that one. Therefore, now we calculate and we find this one. And from here, you calculate your Nusselt heat transfer coefficient. You have the Nusselt number, you know the conductivity, you know the L, you calculate Nusselt number, the heat transfer coefficient. And heat transfer coefficient is 25.177. Therefore, you know the temperature of the surface, you know the temperature of the air, you know the heat transfer coefficient, you can calculate how much it is. Okay, therefore that value. Therefore, now you understand how we use in chapter in building science, we use a heat transfer coefficient. But now we know exactly that the heat transfer coefficient is a function of the velocity and property of the fluid. Okay. For example, if you have water, if you put a Prandtl number of water here, you can see your heat transfer increase much higher. Okay, much higher than this one. Therefore, this is depend on the characteristic of the fluid that you're using. Okay, very important. If you would like to. Okay. Therefore, now we calculate this become around 10 kilowatt. The problem asks you if I increase the velocity double, how much my heat transfer will be. I believe that was the question, right? And I'm sorry, we have to go. What would your answer would be if the velocity was double? If you increase the velocity from 42 kilometers per hour to 84, how much your heat transfer will increase? And they would like to give you some sense that your heat transfer is a function of the velocity, okay? Please calculate it again, repeat it, make sure that you understand every step, okay? Understand what exactly happening, what is Prandtl number means, what is Nusselt number means, and how we are calculating. Please look at it and let me know. Do the calculation, please. I hope you have your calculator, you have no excuses at home, you're at home. What is the answer?
It's a lot of numbers, sir, to put on calculator. Give us a second.
Yeah. Put more gas on it. Again, if we go back, the first thing we have to do, we have to calculate the Reynolds number. Therefore, when you increase the velocity, double, your number will be double, okay? Therefore, here, this becomes that one. Because the length is the same, characteristic of the same, the only thing you increase is the Reynolds number double, therefore you expect this one to become double, okay? Therefore, your Reynolds number become now definitely this value. Now, if you look at this in the border of that equation that we can use, okay? And then we go back and we calculate your Nusselt number. Again, since now we know it's turbulent, therefore here is this value again. This is to make sure that you consider the effect of the contribution of this and that. You can calculate Nusselt number and this one. And you increase the velocity and your Nusselt number increase, okay? Your heat transfer is increased. And when you put in the equation, they come in. Just for curiosity, because I don't have the calculator here, I have a good excuse, but can you calculate the critical length for me? What that means, if I put this on 500,000, I want to know, for example, in this case or the previous case, what is the length, critical length? Can you somebody put it, please do it, please? I want to see how I have a 10-meter long, let's go back to the previous one, 10-meter long plate. I want to see the critical length that the velocity change from laminar to turbulent. Could you please calculate it for me, please? Therefore, X, you're looking for X, kinematic viscosity times 500,000 divided by the velocity, okay?
So we put the Reynolds number at 5,000 to know if it's
500,000. 500.
is.
Yeah. You
Okay.
put is the critical. This is the Reynolds number that you change from laminar to turbulent. This is
Yes.
500,000. You have the kinematic viscosity,
Uh-huh.
and you have the velocity. You can put this velocity, or you can put the velocity for the the first one. Okay, and you can calculate what is the x here.
Okay.
What happened to the rest of the 41?
0.03.
Okay, I do not want. I just want another confirmation. 0.03. It means
In meters.
no, the 0.03. It means 30
Is it?
centimeters.
Is it 50,000 or 5,000, sir? It's 50,000, right?
500,000.
500,000.
500.
Oh, okay, sorry, my bad.
Let me go back. This is the equation that we're looking for. Yeah, this equation. This is 500,000. You have kinematic viscosity. This one. Okay, this is divided by this one. This is 500,000. What happened to the contribution of the
0.3027.
0.327? Okay, what that means? It means 32 centimeter, right? Am I correct?
Yeah.
It means
302, but same thing. 2 centimeter close.
Okay. The rest, do you agree with him? My God. 3, right? I don't have the calculator. I have a good excuse because mine's in my office.
Like a 30 centimeter.
30 centimeter or 3 centimeter. Okay, please check on. It means your velocity, let me go to the other picture. It's easier to visualize. It means this is from here to here is 10 meter. The first 3 centimeter, 30 centimeter, you have laminar, and the rest is turbulent. Okay. Therefore, if you use this equation, or if you use this equation or this equation, this one, the difference will not be that much, because you already the first 30 centimeter, and then you have 10 meter. It means it's dominated by turbulent anyway. Okay.
Sir?
Yes, sir.
Critical includes only laminar and starts at transition or starts at turbulent?
No, critical, it means that at the beginning,
So it starts at transition. Okay.
it is until here is laminar, and after that you have the rest.
Okay.
Unfortunately, most of the time we do not have any equation for transition.
Okay.
Either as a design, either we have laminar or turbulent. Okay. Okay. Therefore, that's the very important. At least you have some idea what that means. This equation. Just don't take them blindly and just mention this equation. Okay. Therefore, we have now equation. We have been able to calculate average. Look at here. This average is the when you calculate, it means the total length of the plate. Okay. And we calculate here, and we find. Again, keep in mind when we're using, we have to calculate the physical property on film temperature. This is called the film temperature. Okay, it's not the bulk air, it's not the surface, it's the average, and that's easy just to take the average of them. Again, the main reason, because this is based on experimental they did in the lab, and they find if they use the average, they get better correlation between these two functions. Okay. Okay, therefore here is the amount of the heat transfer with that. Okay, therefore now you have some idea what that equation means. Again, trying to understand the physical meaning, what that means in the solar number. You have 10,000. That means if you look at from the surface of the plate to the air, you have conduction and you have convection, both of them the same. Okay, the contribution of convection is 10,000 times more than conduction. Therefore, you can ignore the conduction. Okay, if you are dealing probably with liquid metal, the answer will be different because you have very high conductivity. Now, so far, we look at the way the process taking place. That we define the convective heat transfer in general. Let me see how much time I have. 10 minutes. But if most of the problems that we are dealing, either we are looking, the surface has a constant temperature or a constant heat flux, okay? Uniform heat flux. When a plate is subject to the uniform heat flux instead of uniform temperature, the problem that we did it before, last problem, we assume the temperature everywhere on the wall is 12 degrees. But in some cases, probably we have, for example, if you're dealing with a heat exchanger, we have steam, and a steam at a certain temperature, 100 degrees, okay? Therefore, in that case, we are providing uniform heat flux all over the length of the pipe, okay? Therefore, that we can consider here. The local heat transfer is given here is this case. When we have a uniform heat flux, this is the equation comes for laminar, and this equation comes for the turbine, okay? Therefore, again, the same condition. Again, this relation gives value that are 36% higher than for laminar flow and 40% higher in the case of isothermal. If I use isothermal uniform temperature, this expression that I'm using here, it gives you higher value for laminar, but not that much for turbine, okay? Therefore, it's trying to give you that if we change the boundary condition that we have a plate here, if the plate is at uniform temperature or as a uniform heat flux, okay? Therefore, the correlation will change. And here they gave us one correlation mentioned. You can see this, if I use this one, if I misunderstand the problem, and rather than considering as uniform flux, I assume uniform temperature, my answer almost 30% error. If it's laminar. With the turbine, probably the same. Again, in this textbook, it just gives you one example for each scenario. When you're involved in the design, working with SNC level, I'm working for the Ford and big company, you have to go back to the library and look for handbook of heat transfer, because over there they give you more sort of set of equation and for different scenarios. Now, so far we dealt with the plate, okay? Plate. Now let's go for a cylindrical coordinate. It again is the physics again of the problem you have to understand, okay? Because if you look at here, the flow come here. We have only one pipe. We don't have a group of pipe. We don't have a bank. Only one pipe. If you look at here, the velocity until before here is uniform, as we did it in building science when we were trying to calculate the CP value, pressure coefficient to calculate. Air come here, the velocity in the surface here is 0. Velocity, the molecule hit the pipe, the velocity becomes 0. And then we have a profile of the velocity here. And depend on the velocity of the fluid that we have, this separation may take place here, may take place here, or may take place here. Depend on the velocity. If the flow is very laminar, very low velocity, the fluid comes here, touch the pipe, and slowly move back here. As we increase the velocity, this separation take place. As this separation takes place, that means the fluid will jump here and create some recirculation of here. Okay, some recirculation. That means that a fluid going this direction is going back in this direction. Okay. Now, depend on this one, therefore we expect the heat transfer to be different. Let's read. Flow across cylinder sphere is frequently encountered in many heat transfer. An example, heat exchanger. We have pipe, fluid is going here, and air going outside. Pin, sink, okay, that's exactly how it in the case of that we're dealing. The characteristic length, please, the characteristic length for a circular pipe is the diameter. And again, since we know the velocity here, this is the diameter. Even though fluid is outside, as a characteristic length, we use D of the pipe. And the critical Reynolds number, again, changing from turbulent, from laminar to turbulent, is this one, 200,000. Therefore, keep in mind, when calculate for even for external force convectivity transfer, Reynolds number is based on the diameter of the pipe and the critical number now is become 200,000 rather than 500,000. Okay, therefore we have to look at here, and if you look at here, is a very complex pattern that we can see observe, depend on the Reynolds number that we have. Okay, please read it this one. Look at here, at very low velocity, Reynolds number less than 1. We're not talking about 2,000. I'm not talking about 500. The flow pattern will wrap around the pipe and go here. It means if Reynolds number very small, the flow is come down here and slowly move here. Okay, that's the case that we have. At higher velocity, the bonded layer detach, some separation take place, and flow jump over there. And the flow in the back part is by very chaotic, is vortex, and that we can see. Okay, that represents that value. Again, let's go back here. This part we're talking about the vortex form. Okay, and it's very fluctuating. There is no constant velocity. It just is circulating that vortex that we have. Okay. Any question, please? Any question, please? Now let's look at visualizer that I mentioned. We are doing most of the time experimentally. This is representing this sort of CD, but just we would like to show you, the whole idea will show you that how behavior will change as a function of Reynolds number. Okay, therefore, as I mentioned, it's very, very sort of complex. If it's Reynolds number less than 0.1 cubic flow, around 10 Reynolds number, separation start to take place. And if it's more than that, we have vortex shape behind it. Okay. Around this range, the bonded level come here. Okay. Around laminar to okay. Therefore, you can see the behavior is changing. That's applied to it. Cylinder and sphere. Because we are using characteristic length for both of them for Reynolds number. For the Reynolds number here, it doesn't matter. It's still a cylinder or a sphere to use a parameter. Similar behavior we can see for Reynolds number. Okay. I will stop here and I will wait to see if you have any question, any comment, any suggestion. Any comment about tutorial? Any comment about substitution? Any comment about your project? Are you still there?
Sir, for the equations, we have different conditions laminar and turbulent, right?
Yes, sir.
You mentioned there is a single equation for wall condition. I thought
I did mention that there is one equation that if you are dealing with the sort of flow over a plate, and that equation, if you look at here, this equation considers the effect of turbulent flow and laminar flow. Okay. Look at here. I'm so sorry, I'm going back and forth. Look at here. Flow overlay your vertical wall or horizontal. Okay. You're going to parallel to the plate. Okay. And it is going to parallel to the plate. Wall and the flow is in this direction. In this direction.
yes.
Okay. And therefore, at the beginning, as we saw before, the flow is laminar. And after that, there is nothing to control. It's one layer. It is one layer from another. Okay. Because there's nothing about at the top that forces you to sort of stop. Here we have a laminar flow and we're talking about flow. The question is, how much is the contribution of laminar flow compared to the flat flow? Okay. For that way, we can discuss this. We can calculate this length. The length of the plate from here to here. Okay. And you can calculate from here to here if all of them are laminar, from here to this laminar. Therefore, this equation is satisfied required from X to 0, X and that's nominal, because it's not really a little turbine. But that is too big. You have push motion nominal, and push motion transition, push motion turbine. Now, the question is, for example, if you have a 10 meter plate, 5 meters, 5 meters laminar, 5 meters turbine, both of them will be meters. One portion laminar and one portion turbine. In that case, I suggest that we use this equation about half.
Okay.
Getting both contribution from both of them.
Yes, thank you.
Thank you, sir. Anyway, the lecture is over. And here, if you have any question, please do ask.
Did you go over the slide where you explained for the project from day 1 to 5 and time 1 to 20? Can you explain how we estimate temperature and node like that again, please?
No, it's just wait because I found my line. Just a second, please. Chapter 6. We mentioned here, this one here, this one here, the wall. I mentioned consider the mass of the wall, the equation, and so on. And then we have all those equations, and we calculate and so on. Before, when we were doing it, we were doing like this, project number 1. It started from midnight, 1 o'clock in the morning, until 24 o'clock. We calculate about the temperature, and coming back and calculating each temperature T1, T2, T3, and so on. Okay, because you were not only because you were assuming steady state, therefore you did not have this term that we have here. But now, when you look at your equation, you are trying to calculate 1 o'clock, but you need the temperature when it's at 24. You would like to calculate the temperature at 2 o'clock, but you need the temperature at 1 o'clock. For every time when you finish at every hour, for example, when you start at 2 o'clock, you come down here, you put all those temperature at 2 o'clock, I'm sorry, T plus 1, this has to go the other way. You have to put T plus 1 here. Okay, I made a mistake. All of them in this one, okay? You keep the old temperature, because when you're going to 2 o'clock, okay, when you're going to next time, you need to know the previous temperature. Therefore, you put the temperature at 2 o'clock here, and all, then you go calculate the 3 o'clock. When you go to 3 o'clock, you need the temperature at 2 o'clock. This temperature is 2 o'clock, okay? Now, this was what you're doing for 1 day. They're exactly the same as before. But the only thing that you have at every time you keep record of all the previous temperature. Is it clear here?
So when what's at the bottom there is
We put all the temperature. Yeah, all of the temperature put here. You keep record of that. Because, for example, as I mentioned, if you go and calculate the temperature at 5 o'clock here, this is 5 o'clock, 4 plus 1. You need to know what was the temperature at 4 o'clock. Therefore, you have to keep all those temperatures here. And then you go calculate 6 o'clock. In order to calculate 6 o'clock, you need the temperature at 5 o'clock. This, you have to keep track of all the previous temperature because of the initial value. As I mentioned, when you would like to calculate at 1 o'clock, you need to know what was the temperature at 24. You do not know because you're just starting the program. Therefore, we assume at the beginning some temperature. Some temperature, doesn't matter what temperature it is. But when you go through this loop from time 1, here become at 1 o'clock in the morning, you need the temperature at 24 hours. Okay, therefore you put this temperature here, this initial value. When you calculate the time equal 2, this becomes 2, you need the temperature at 1 o'clock. You already calculated temperature at 1 o'clock, you keep the temperature here, and then you go back. But since we assume some random number at the beginning, we would like this to call it initial value. This effective initial value will pass after 3 or 4 hours, maximum 5 hours, 6 hours, okay? And depend on the mass of the ball we have. And then your result makes sense. But in order to make sure that you run it for 5 days, 3 days, 4 days, and you can look at the data at any point for today and tomorrow. When you look at the data, you see the difference between temperature at node number 1, for example, today and tomorrow is at the same time. It's less than 0.5 degree. You can mention it's converged. Did I answer your question, ma'am?
Yeah, so we don't need to do for 5 days. We just do until we have something that makes sense.
Yeah, that's right. And the way we do it in the programming, because in order to program stuff, it doesn't need to go 5 days. For example, I take the temperature of node number 10, one random temperature. At a specific day, I keep track of it here. I keep it track it here today. Mention temperature at node number 15. On the first day, it was, when I calculated at 3 o'clock in the afternoon, it was 16.65. And then tomorrow, at the same time, for the temperature node number 15, at 3 o'clock in the afternoon, I compare today with tomorrow. If the difference between these two is less than 0.5, it's converged. This is the way we do it in the fourth run, okay? Therefore, here I keep another value here for a given time, a dimension. If the time is 3 o'clock, keep temperature, record of the temperature at node number 15. Then tomorrow, at 3 o'clock, at node 15, I have another temperature. I compare these two temperatures together. If the difference between them is less than 0.5, I'm measuring it's converged. Why less than 0.5? Because the accuracy of the thermostat, the thermocouple is around 0.5 degree. This is the way we do it in the program. But if you like, you can run it for 2 days and just look at the result and say it's converged. Did I answer your question there?
Yeah, thank you.
No problem. Any other question? I send you the solution to chapter 5. This Friday, I will send you the solution to chapter 6. Please do it. The reason I'm not putting on noodles or I'm not sending it earlier because I want to make sure you study, you do it, and then I will send it to you. Read the chapter, please, because this is your future, okay? You have to have a complete understanding of the physics of the problem. It's not memorization. If you have any part that's not clear to you, come and ask me. Ask the TA. You have excellent TA, they can explain it to you, okay? Try to understand the physics of the problem. It's not memorization, my friend. Any question? Anyway, I'm here. I put myself off. If you have any question, please do ask me. I'm here. I'm here for the next 10 minutes doing my work. If you have any question, please just call my.
Thank you, sir. Have a good day.
Thank you, sir. Have a nice evening. Enjoy it. The winter is coming.
Sure, I have another question.
Yeah, yes.
The initial temperature we estimate, it absolutely doesn't matter what we choose, or is it better to choose something that is far off from what we think it will be or closer to what we think it will be?
It absolutely doesn't matter. Absolutely. Because as we go through the time, the number will be corrected. Okay? And, and that's depend on the mass of the wall. If the mass is not that high, it will converge fast after 2 hours. If it's very massive, probably takes 4 hours. But the first day, after 6-7 hours, it will finish. It doesn't matter. Just I mentioned that's why I put such a ridiculous number there. Minus 20,000, 200,000, minus 60,000. The effect will disappear. If your program is correct, the effect disappear after 5, 6, 7 hours. Okay? Therefore, that's they call it initial value. But if you go through the time, the effect of initial time will disappear. You see, when we are dealing with the differential equation, we have initial value and boundary condition. Initial value is only effect on the first part of the problem. After that, disappear. Therefore, put 6 million, put plus 1 billion. You will see, just for your curiosity, put those numbers and you see how this effect disappears. Has no effect whatsoever. About your end result, because the next day the initial value disappear. Effect is in, and then the effect of the temperature and solar radiation will show in your result.
Perfect. Thank you so much.
No problem there.
Have a good day.
You too, dear. Stay safe.